weird. So here's the limit I want you to think about. Limit as x goes to 0 of the cosine of x minus 1 over x. That's the limit. So play around with that for a second, see what you get, and then I'll show how I would approach it. Lex, try that.
Well, this can 1 minus 1 but you plug in zeros to the bottom.
What does it look like?
It looks like
0 or 0 over 0?
0.
Yeah. Okay, so if it's 0 over 0, might there be a limit?
Yeah.
Yeah, there might be a limit. Okay. So what are we going to do next?
See if we can do cosine of x over x. Maybe minus 1 out of it.
So rewrite it like, let's see, cosine of x over x. And then that would give us a minus 1 over x.
Yeah.
Okay. So if we reevaluate this, what's going on with the first fraction? We have 1 divided by 0 when we try to plug in, which does not exist. And what about this over here? 1 over 0? That also does not exist. Does that mean the whole thing does not exist? The answer is no. We saw an example like that the other day where we did some algebra and all of a sudden it did exist. Okay. So this right here is useless. That's a dead end. Okay. What else can we do? What was that? Whip out Desmos and graph it? That's a great idea. Let's whip out Desmos and graph it and see if maybe there's a limit according to the graph.
Algebraic.
We'll get to that. Yeah, but I love doing numerical stuff first.
Okay.
Yeah. Because maybe that'll give me a hint about the algebra sometimes. Sometimes it doesn't, but maybe it'll give me hope. All right, Desmos calculator. I'm going to enter it as a function of x. It's a fraction. Cosine x is 1. Use parentheses, please, in the proper places. Divide by x. And it looks like it's going through the origin. When x is 0, it looks like y is probably 0, but we know for sure what is f of 0. Undefined, does not exist. Yeah. Okay. But it looks like there's a limit. Okay, so we can zoom in just to make ourselves feel better. I wonder if the computer would like eventually crash if I tried to do this for an hour. Probably.
I think you should try it.
Yeah, not today. Soon, when I'm really bored, if I don't feel like Netflixing. Or scrubbing the toilet, something like that. All right, so it looks like it looks like the limit is 0, right? So, and we could numerically check f of 0.1. It did crash on you.
Yeah, you just gotta
you can crash it in a few seconds. F of 0.01. F of 0.001. And I can see it looks like there's a numerical pattern that's getting closer to 0 in a kind of systematic way. All right. So, question. Is there always algebra to solve one of these? Answer, no, there isn't always. Some problems are not algebraically solvable, and the only way to do it is with some computer program, which we happen to have here. But turns out there is a little algebra that we can use. Turns out this problem is a lot like the problem we did the other day. It was something like the limit. We had something like the square root of x blah, blah, blah. Let's say minus 2 over, what was it? I think it was x minus 4 as x went to 4. And if we plug in the 4 here, we're going to get 0 over 0. But we did some algebra. What was the algebra we did on that? Anybody remember? We multiplied by the conjugate of x minus square root of x minus 2, which is the square root of x plus 2. And it turns out there's something like that we can do with the cosine also. All right, so here's what we're going to do with the cosine. So new page. I'm just going to whip out a little algebra on this. I'm going to forget about the limit for a minute and just look at cosine of x minus 1 over x. And what I'm going to choose to multiply by is the cosine of x plus 1. And I have to do that in the bottom too.
So x cosine x times x plus x.
So it'll be, yeah, I'm not gonna, usually I don't distribute the
Oh.
bottom because the top is where my real trouble is. So I'm just gonna distribute the top. Now this is a difference of squares. The middle terms are gonna cancel. So that's gonna give me a cosine squared of x minus 1. And the bottom, I'm just gonna leave it as x times parentheses. But you can multiply it out, it doesn't matter. Either way is fine. Plus 1 in the bottom.
Oh,
Okay, why is this better? Anybody recognize the numerator there?
that's an identity.
That's an identity related to the Pythagorean identity for trig. So the Pythagorean identity says that the sine squared of x plus the cosine squared of x is equal to 1. So if I whip the cosine over to the other side, I'm going to get the sine squared of x, oops, too many parentheses there, equals 1 minus the cosine, which is almost what I want. So what's my numerator equal to?
Negative sine.
Negative sine squared, yeah. So it turns out this right here is the negative sine squared of x over x times cosine of x plus 1. And that solved my problem.
Denominator is still 0. I should just try to plug it out.
Oh,
Yeah.
This does solve my problem. Check this out. So at first glance, it looks like I have more of a mess than I had before. But do you remember the other day in class, we looked at the sine of x over x?
Yeah, it's 1.
That's 1. Okay. Isn't there a sine of x over x hiding in here?
Yeah, it's
Okay.
what the identity of cosine x.
And then so we pull out one of the signs in the top. That's going to leave another sine of x in the top. The x is there, so over here I'm going to put the cosine of x plus 1. So this blue version is another way to write the green version, except I missed my negative sign. We'll throw it there.
The negative 1.
Yeah, so now this fraction right here, if we take the limit as x goes to 0, this sucker right here is going to go to a negative 1 because of the negative in front. What's happening to my other fraction? What's the sign at 0?
0.
Is 0. Yeah. So sine of 0 is 0. What's the cosine at 0? 1. So my denominator, this is going to go to 1 plus 1 or 2. So then my answer, I think, might be negative 1 times 0 over 2, which is 0. So we have a rule that says you can split the limits into a multiple of limits if both limits exist. Does negative 1 exist as a real number? Yes. Is 0 over 2 a real number? Yeah, so this was legal. So we just found out that our original limit ought to be, just like Desmos said, 0 this time. Now the limit equals 0. Does the function equal 0 there?
No.
No, it does not. There's a little hole right there. No. That was some fun trick.
Would you have to solve it would you have to times it by the conjugate in the first place? Or no?
Well, I used the cosine plus x plus 1 as kind of a conjugate.
Yeah.
Yeah, and the identity from the Pythagorean trig theorem helped. Yeah. So that is, yeah, so in this case, I didn't have to whip out the geometry like I did the other day to do sine of x over x, but this algebra helped me work out. Now, how many tries did it take me before I got this right the first time? 10. I got it right the first time here now because I did it before. Okay, so keep that in mind. You see me do things in class and you're like, oh yeah, okay. But when it comes to doing it on your own at home, if you haven't done it a ton of times before, you're like, oh shit, what's going on here? It's hard and you're gonna get dead ends, and that happens. And we'll just get more practice and get better at it. All right, so that's the example I wanted to do from, so that's kind of like the stuff we were playing with in section 1.3. let's talk about section, no, that was section 2.3, right? 2.4 is what we're doing next. Got my notes. Yeah, okay, so 2.3 was limit laws, just playing around with when can you find a limit, when can't you? As often as possible, we want to find some algebra that leads us to it, but sometimes there just is no algebra, and so we have a backup of using something like Desmos to see if there's a pattern. Next. We're jumping a little ahead. Section 2.4, continuity. So continuity just means there's no breaks, is one way to think about it. So when I graph straight lines, like y equals mx plus b type stuff, continuous. I can draw it without having to lift my pencil. Polynomials, like our favorite parabola, y equals x squared. Right? I can draw as much as you want without lifting my pencil in one shot, continuous. Remember, y equals the absolute value of x? What's that look like? It's a V-shaped graph, yeah, so it looks something like this. I can draw it without lifting my pencil. Even though it has a sharp point, it's still continuous. It turns out absolute value is a piecewise function. We talked about piecewise functions before. They're ones you have to graph in two parts. So this is how computers think about it. So the piecewise version of the absolute value of x is to graph y equals x if x is greater than or equal to 0. And you graph the line negative x if x happens to be less than 0. So if I just kind of redraw this from this point at the bottom up that way, that's y equals x. And the rest of it in blue would be the part of the graph of y equals negative x. Agreed? So that's the piecewise version of the absolute value, which is how it's programmed into a computer. Okay. Next, tell me about the slopes of this. Is like with a straight line, the slope's always the same. With a parabola, right, it's shallow at the bottom, steeper on either edge. What's going on with the slopes on the absolute value?
Well, change.
It slope changes in the middle, yeah. So what's the slope on the left side? -1, right? What's the slope on the right side? Oh, it's hurting me here. The slope on the right side?
1 over 1.
1 over 1 or just 1, yeah. So if I wanted to write a slope function for this, it would be a piecewise function. So I would say the slope is -1 if, I'm just going to write it in reverse, if x is less than 0. I'm going to put that part first. And I would say the slope is +1 if x is greater than or equal to 0. But I got a slight problem with that part.
It doesn't go straight down too.
No, it doesn't in this case. It just, either the slope is -1 if you're on this side, or the slope is +1 if you're on that side over there. Now, if I pick any point in the red area here, I can pick a point nearby and show for sure the slope is 1. If I pick 0, I can only pick a point to the right to identify the slope as 1. So at 0, it's a little sketchy. So sometimes people say for the slope function, they get rid of the or equal to. They say, that part's not, that's a little weird. We're going to ignore that one. And sometimes they include the slope as 1 at 0. So there'll be some variation depending on what computer we might use to play with this kind of thing. I'm going to graph the slope function. So y equals that as a graph. Let's say here is +1, and then down here is -1. So then let's graph it in blue. As long as x is less than 0, the slope is always -1. but at 0, it's not. So I'm going to put an open circle there. So that's a graph of y equals -1 only for those x values. Now to finish the graph, I have to say, okay, now we're going to let y equal 1 for 0 and beyond. So that would go like that, right? And should I put an open or a closed circle there?
Close.
Maybe a closed circle here. Yeah. Is this graph continuous?
No.
I had to lift my pencil a bunch of times to make it happen. Okay. So just a note, this is not continuous. So it's not continuous because it's got that break. All right. Let's go back and look at a function from yesterday. Let's say we look at the function f of x equals the sine of x over x. And my recollection looking at that graph is it looked something like this. And it had a peak right here at -1. All right, I'm going to double check on Desmos, make sure I didn't screw that up, but I think that's what it looks like. Turn that one off. Call it g of x here equals sine of x over x. And hope I have the wrong scale, so let's go back to the home page. And I have a different, my one is a lot higher, so I have a higher peak there. But if you'll notice, the wave does dampen, right? It's less, has less of an amplitude as we move out. Is the point. Okay. So my drawing's not too bad. Different scale, but similar.
That's a peak at 1.
Yeah, there's a peak at 1. Now, however, though, what is g of 0? No, the peak is at, well, yeah. So for x equals 0, the peak is y equals 1. But there's a problem there. Do we actually attain that peak? No, it's undefined there. Okay, so my graph is not correct. What's wrong with my graph I drew on paper? I draw it as being continuous through the point 0, 1, and it ain't.
There's a hole there.
There's a hole there, so I'm gonna have to put an open
So
circle
you have
there.
to open circle.
Yeah, so there's an open circle there. So this is not continuous. And instead of not continuous, we often say discontinuous.
Discontinuity. Yeah.
Discontinuous. Okay. So there's different ways to be discontinuous. We could have just a little hole for discontinuous, or we could have a break for discontinuous, like this line graph over here on the bottom left. Okay. So a couple ways continuity happens. Now, what is it? So this is all intuitive stuff, right? We're just talking about moving a pencil. There's a mathematical definition of continuity, so I'm going to give you that next, and we'll look at some homework problems. So to be continuous at a point, we have to have one f of whatever that point we're looking at. I'm going to call it A. F of A has to exist. It's got to be a number. It can't be undefined. 2, the limit as x approaches A of f of x has to exist. There's got to be a limit. That has to exist too. I right there. Oh shit, I got too many letters in there. Exists is that's how you say it in Latin, I think. I have no idea. I just like to make shit up. My grandpa taught me that. He was really good at it. And then third, that limit has to equal the function value. And you could say, well, why not just state that third line? Because really that's the essence of it. stating that third line implies the first and the second had to be true, otherwise there's no point in stating it. Right, so I just, that's the complete way to state it. Right, but this is the meat of it right there. The limit has to match the function value. Okay, if it doesn't, then it's discontinuous at that point. So then that's just a single point. When we draw a function, we draw a ton of points, right? Dragging our pen across the screen or across our paper. So to exist in more than just a point, we talk about existence in an interval. And generally, we talk about an open interval. So that would be something like from x equals a to x equals b on a number line. And super simple, it just has to exist at each point in the interval. Or be continuous at each point, follow that at each point. Each point within the interval. Notice I'm ignoring the endpoints here. So when we talk about limits, it's got to be both ways. If we're at an endpoint, that means we can only approach one way. So endpoints have to be treated separate by just looking at one-sided limits on each side. So that's just special cases we look at later. All right, so we've seen two kinds of discontinuities. We have a break, which is also called the jump discontinuity, right? We have a hole, which is often called a removable discontinuity, right? Because couldn't I just plug the hole? Can I just fill it in? Yeah, if I fill it in, it's now continuous. So I could rewrite this function as a new function. Let's call it capital F of x. And it would have to be a piecewise function. It would be the sine of x over x if x is not 0. Because that's great, works fine. What do I have to do when it is 0? Well, I just have to pick a number to plug the hole with. Well, what's the obvious number we should use to plug the hole? 1. And sorry, that's supposed to be a mark on the line. So we would just plug in 1, that's it. If, oops, extra line there. This capital F of that function is continuous because we plug the hole. So if the hole is pluggable, it's said to be a removable discontinuity. Can I plug that hole? No, it's not pluggable, right? If I try to fill in that dot, it's not a function because then we're saying for this x, there's 2 possible y values. Sorry, I can't do that. And if I tried to make a vertical line there, well, a vertical line is not a function either. This is not fixable. Okay, not fixable. So the removable discontinuity, I'm just going to put that on another page. We have a situation like this. We have f of a does not exist, but the limit as x approaches a of this function does exist. So L is our plug. So we would just plug the hole with the point AL. That means we have to redefine this as a piecewise function. A big whoop, a little more ink. All right, one more example, and then we'll take a look at some homework problems. Think about the function, what should we call this one? We're going to call this r of x equals 1 over x. Based on your memory, make a rough sketch of that before you hit Desmos. You remember what that looks like? It's been a while, maybe. Let's see. If x is 0, can't do it. If x is 1, y is 1, right? 1 over 1, so I get a point like right there. If x is 2, I would get 1/2. 3 is 1/3, so this drops down that way. If I pick a number like 1/2, it's going to jump up to 2. 1/10 would jump up to 10. So it does that right there. I looked at this in class a couple of days ago, I think. And then where's the other part of it? Quadrant 1, 2, 3, 4, 3 down here. Yeah, so something like that. Not the best sketch, but something like that. And we have asymptotes. So I have this line right here is the line x equals 0, and that is a vertical asymptote. And then I have this line over here, which is the line y equals 0, and that would be a horizontal asymptote. Oh, did I tell you guys I used to not like math?
In high school?
I had this high school teacher who drank a lot of cough syrup during class, and she made fun of me one day for calling a parabola a parabola. And I was this skinny, shy kid sitting in the middle, and I was so embarrassed when she started laughing at me in class when I said, she asked her, "What is this?" And I read ahead in the book. I was like, "Oh, it's a parabola." Like, ha 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 ha. Oh, what is the cough syrup?
Yeah.
Cough syrup has alcohol in it. So she was swigging cough syrup between classes to get a buzz. That's my belief. Okay. You don't live long doing that, so please don't try it. Anyway, so then later I went to college, community college, and I was going to major in business because my dad was an accountant. I tried accounting, hated accounting. Oh my gosh, it was so boring. My dad liked it. Bless you if you love it. That's great. So I did a year of accounting. I said, this sucks. So I changed my major to marketing, maybe. I did marketing for a bit. But then I had to do kind of public speaking classes, and I hated that. So that was, I don't want to do marketing. I was going to do business administration. So now I'm in my 3rd year at the community college, and I get this letter in the winter in the mail saying, hey, if you don't take a math class, we're going to kick you out because you can't get a degree without a math class. So now I'm in my 3rd year. I still haven't taken math. I hate math since my 9th grade algebra teacher. And so I said, what class do I need to take? And they said, you have to take business calculus to get that degree. I said, great, I'm taking business calculus. They're like, well, no, you're going to take the previous classes. And I had gotten a little bolder at that age, and I read the catalog. I said, it doesn't say that in the catalog, that you have to take these other classes. But you should take the other classes. It doesn't say in the catalog. So they had to let me in business calculus. And it wasn't as hard as this class because we didn't do as much algebra. And the teacher started talking about asymptotes in this great deep voice. And I was like, holy shit, asymptotes, this infinity idea just blew my mind. I was like, oh my God, this is way more fun than marketing and accounting. I was like, I'm going to be a math major. So then the next year I went to the 4-year school and I took my first calculus class, not realizing you're supposed to take trig first. And after the first test, like I wrote this nonsense down from the test for trig because I had no idea what sine and cosine were. He said, drop the class, change your major. I was so mad. I went to the library, I got a trig book, and I studied my ass off. And I went from failing the first test to getting an A in the class. But I had no life. Like all I did was study both at the same time. Anyway, my point, I didn't used to like math. Now I love math. I didn't even know I was good at it when I was in my first 3 years of college. And the thing that turned my life around was asymptotes. Changed my life. Anyway, so asymptotes are beautiful things. I love them. Back to the problem here. So what is the limit as x approaches 1 of 1 over x?
1.
It's just 1. Yeah, you can plug in 1. It works nice. The answer is 1. Okay. What is R of 1? It's 1. Therefore, this is continuous at 1 because they match. All right, because those two match, continuous. It's continuous in a lot of places. What about the limit as x approaches 0 from the right side of 1 over x? We could say it's infinity because it goes up forever there. Could we say does not exist? We could, but infinity is a better answer, right? Because it implies two things. It doesn't exist, but it goes up forever. Okay. So you could say it does not exist, but a better answer is infinity. Limit as x approaches 0 from the left of 1 over x. Negative infinity. Okay. Limit as x approaches 0 of 1 over x. Yeah, you can't do plus or minus. It just does not exist. Because the problem if you say plus or minus, you're not making it clear which it is. So the best we can do here is does not exist. If you wanted to say plus or minus, you really have to expand it into the two cases to be precise. Okay, so we have the limit doesn't exist. F of 0 does not exist either. So then, since both of those don't exist, all we need is one of them to not exist, then it's discontinuous. Right? If they both don't exist like this, not always, but it often is called an infinite discontinuity. Because we're going to infinity. So at x equals 0, we have an infinite discontinuity. So we have three kinds of discontinuous. We have jump discontinuity or break. We've got removable discontinuities where we can plug a hole. Sometimes there's a lot of holes to plug, depends on the function. And then we have infinite discontinuities. Those are the things that can happen. And the homework's just getting used to that idea, the formal version of continuous. All right, so I heard there's some homework problems people were curious about.
But you want to start on 2.3 first?
You still have 2.3 questions?
No, I have two.
Okay, let's go. Does anyone have a 2.3 question? I'd asked earlier, nobody claimed to have a question. Asking one more time. Going once, going twice. Gone, on to 2.4. All right, what do we got in 2.4?
Number 10.
This should be interesting. Oh yeah, this is a fun one. This is where we get to play a game with can we make it continuous? All right, give it a try. All right, so this one is a little harder, but not too bad. Add to the page, please. All right, so I'm going to start by making a graph of what they have there, and we'll go from there. So let's see. Let's go blue. Get some axes. And there is a way to plug that into Desmos, but that missing B is kind of a problem. Oops. All right, so let's see. X equals 4 is of interest to us. So usually when I'm graphing one of these, I make a dotted line at the X value. That's not a very good dotted line. Not doing so good here today. Boom, boom, boom. Okay, so there's X equals 4. So I'm just reminding myself I have to do something different on one side than the other. If X is less than or equal to 4, then I have 5X minus 2. Okay, so minus 2 would be down here somewhere. And then from there, I just want to go, might run out of room to do this, up 5 over 1. And then I'm going to keep doing that. So for sure, I know I have this point here and that point there. So I'm just going to make a line through them. So it does something like this. And I should have made my scale a little bit different. I'm trying to get to the point where I'm going to hit this vertical line. What value am I going to hit at? If I plug in 4, I'm going to get what? 20 minus 2 is 18. So these two are going to collide up here at the point 418, right? So that's the left half. Now the right half, I know what it means to have a slope of -6, but I don't have a b to start at. But if I want this to be continuous, don't I want to basically go -6 from there? Like that? And I just have to make sure m equals -6. That's what I want to happen to be continuous. Agreed? Okay. Do you remember the point slope form of a line? I mentioned it in class the other day. That's the y minus y1 equals m times x minus x1. So if you know the slope and you know a point, you can figure out what the line is in other ways. What slope do I want to have here?
Same slope on the other side.
Well, no, I want it to be -6, right? Because it's given there. Yeah. So I want m to be -6. Do I know a point on that red line? Yes and no. Turns out I want it to start there, but with an open circle. So without this condition, it would have gone through that point. So I want this red line to basically come from the point 418. So then I just fill this in. Now they want me to figure out what B is, so then I have to just do some algebra to figure out what B is. So clean that up.
Can you just take the two equations that are equal to each other and
And
plug in 4?
Plug in 4, yeah. Yeah, I'm just doing the geometric version of that.
Wait, just to make sure the slope is 5 and of the first one is -6 on the next.
Yeah.
Okay.
Yeah. So that's why I want to figure out what line this is. I know it's going to have a slope of -6, so that's why I put that for m. And then if I want it to be continuous, it's got to head toward that point. So I'm plugging that point in. And if I clean that up, I'm going to get y equals -6x plus 24. And then I'm going to add the 18 to the other side. So it looks like B is going to be what? 242 for my version. And Austin, right? Austin, bless you, suggested that if we want these two to meet, they got to be equal. So if you take the 5x minus 2 and you set it equal to the -6x plus b, you want them to be equal at 4. So then you just drop in a 4 for x. And then solve for b. That'll do the same thing. But one thing that I learned when I was studying calculus, if I can think about things algebraically and graphically, then I have more tools to figure stuff out when I'm really lost. So as much as possible, I try to do algebra and graphical stuff to put it together. So we have a couple of different options to solve this one. So let's see, does that work out? This is going to give me 18 on this side equals -24 plus b. Yeah, add the 24 over and we get the same thing as b. We get b as 42. That was fun. Want to see a cute trick for this one in Desmos?
Yeah,
You can always say no. Sometimes my cute tricks are ridiculous.
sometimes they're not so cute.
Sometimes they're not so cute. Yeah, so I get the cute thing from, I had this teacher when I was in graduate school for math. He'd come to class and say, he's this old guy, he'd come in giggling, oh, I got a cute problem for you guys today. And if he said that, you knew you were in deep shit. It was going to be hard. So I adopted cute to make myself kind of get over the hard hump and try and get it done anyway. All right, let's reset this. And then I'm gonna do it in, let's see, 2 parts. I'm gonna do the first part as the top part, which was what, 5x minus 2 for me? And get that on there. And if I want to restrict the domain to make it end at a certain place, then in front of it, I would have to put a parentheses and then type the restriction, which was, well, I think x less than or equal to 4. And then I think it's a colon or a semicolon. Colon? That work? Yeah, it's a colon. So when we write down notation for piecewise, we do the equation, then the condition. Here they do condition, then an equation. Then I'm just gonna, remember how I did variables the other day? So I'm just gonna pick B and let's set it equal to 0 for now. And that's gonna give me a variable. And then I'm gonna type the other one as g of x equals negative 6x plus b. And I can see that they don't meet. But all I have to do is adjust b to make them meet. I can see b must be much higher. So I could just do something like pick a bigger number. Let's see. By looking at this, I can see it's got to be higher than 20. So I could just guess at like 30. And then I can play with the slider. 30 isn't far enough. Maybe I'll go up to 100. It's not 1,000. And then I can just kind of play around sliding it until it meets and try and figure out what number that is. Kind of fun. So like Lex was having fun with the wheel on the mouse and Desmos making it crash. There's all kinds of cool things you can do with Desmos and variables. Oh, look, I got lucky, 42. Look at that. Holy shit. It's pretty cool. All right, let's see. Anybody else have another specific homework problem? Otherwise, I'm going to pick
11.
11. All right.
Oh, that's the.
This time the M is missing, but it's the same procedure will work for this one too. Yeah. So we can use a couple of different tricks on this. I'm going to take Austin's approach. Page. So since we want it to be continuous, the 2 parts have to match at the given x value. So I could type m times negative 8, because that's the x value I want mine to match, minus 16, has to match, oops. And I'm just going to plug in for x, negative 8 squared plus 3 times negative 8 minus 8. And if I clean that up, out will pop what m has to be to make that work. Solve for m.